Welcome back, everybody. I just wanted to give you a few messages before we move on to the solution of the exercises. So I wanted to wrap up a little bit about the elliptical orbits, and I also want to give some few hints about the exercises and what kind of things you should expect from the solution in the Cartesian coordinate system and the solution when you deal with the radial degrees of freedom only. So I'm going to sneak in some 10 minutes, and after that, we will just circle around. I guess Shu-Yu will take care of the people online, and I will just float around, and Abby is coming roughly at 4 o'clock. And feel free to hang around till 5 o'clock if you wish to, if you have the possibility. It's always a pleasure to chat with you guys. I will probably have to go 4:15 today because there's a PhD defense where I have to, which I have to tend to, but Shu-Yu and Abby will hang around. And finally, they can just get rid of me and there will be some peace. Okay, guys, I just wanted to say a little bit about the numerical part of this homework. And this part which you see now is something which we are going to use when we begin with the midterm next week. So the way we are going to also discuss the midterm is that we will gradually bring in the various elements from the lectures into the midterm. And you should feel free to view this midterm again as a kind of dialogue. So it's the learning process and understanding and how we develop a code for the solar system, which is going to be the important topic here. And on the way, we are going to look at many of the same things which we did in the previous midterm with energy conservation, angular momentum conservation, see that the forces which we deal with do obey these properties, and that when we solve the problem, that actually these things are seen in the solution. So we are going to have roughly 2 weeks for that midterm. So we will use next week and the week thereafter, both on Wednesdays and Fridays, but you should also feel free to bring up discussions about the midterm whenever you want. Okay, let me say something about the exercises this week. And this is in particular about exercises 2 and 3. And you, in a way, you have parts of the solution in the lectures from this week, the lecture material. So one thing you can do is to plot this harmonic oscillator potential. And just keep in mind that this potential now is us transforming a potential in Cartesian coordinates, which goes like x squared plus y squared, into polar coordinates. And then we bring in the radial dependence from the kinetic energy into the potential. And that gives us what we call an effective potential. So in a way, you can think of this as you, instead of plotting this in 3 dimensions with x squared and y squared, which gives you a potential value, this is something which hopefully can give us a better insight about the physics of the system. So like, if you are like me, hopefully not, but that would be a horrible fate, wouldn't it? But the thing is that I often find it easier to extract things if I have something in 2 dimensions only. Okay, so the next thing is to solve the problem when you have found this minimum point, which is this point which you see here, but then use that one as an initial value for a calculation in 2 dimensions. And in 2 dimensions, the general solution is just given by cosines and sines, and they separate in x and y. So actually the harmonic oscillator, making a transformation to polar coordinates or spherical coordinates in 3 dimensions is an overkill, because the problem separates well in Cartesian coordinates. So this is the preferred frame of reference for coordinate systems with which you solve the harmonic oscillator type of problems. And the code, which you see in the lectures here, if you just scroll down, this is tailored to a 2-dimensional problem. And you see that here because I define a vector as a matrix of dimensionality n, which is a number of time steps, which we set up here based on the initial time and final time and the time step. And then there is the x and y the coordinates. And as usual, I always put all constants equal to 1. And then I get a r min, which is defined in terms of the angular momentum. And this is the expression which you derive in the text. And then I put x0 to r min, and I put y0 to 0. And that's a pretty convenient choice, because else you would have to deal with the square root of x squared plus y squared. So it's convenient to actually put x to some value and y to 0. And that means that the velocity is going to be perpendicular. It's going to be in the y direction. So, and in that case, you would simply then put the velocity in the y direction. And you have a y0, which you also can calculate in terms of this square root of omega times r min. So these are the initial values. But now pay attention to one thing. So in this particular case, your acceleration is just the negative position in x and y multiplied by the frequency squared, the natural frequency. So that's your acceleration. When you change this to polar systems, then you need to take into account this centrifugal barrier. And that changes the expression for the acceleration. So just keep that in mind, that when you simplify it to the one-dimensional problem in polar coordinates, then your acceleration changes form, or the expression changes. Now, when you run the calculations here, depending on your step size, what is going to happen then is something like this. So your x and y follow this cosine and sine behavior, and they are opposite phase. So when x is 0, y is 1, that means that the radius is equal to 1, and you see the value here, 1, but then it has a small error. Now, this behavior is something you will have to live with, because you have a finite time step. And there will be small imperfections in your reproduction of a cosine and sine. And the fact that the solution oscillates, when you add them up, that's going to give you a small imperfection. And you see that because it oscillates within an envelope of 10 to the minus 7 plus 1. So ideally, you should have 1 exactly, but you see now you get 1.0001, right? If you then change to polar coordinates, which is the next topic, if you just scroll down here, now there's another code example which hopefully can aid you, and I hope you don't get offended if I give you all these kind of hints. Here we have again R0, which is R min, so we're looking at circular motion only. But now we have to be a little bit careful, because the acceleration now contains this centrifugal barrier term, this L square term, divided by the radius cubed. So when you made the transformation, you have now an effective force which contains this term from the kinetic energy. And you need to plug that in to the expression for the acceleration. So there are pros and cons in solving problems in Cartesian coordinates and in another coordinate system. So just keep that in mind. And the physics should be the same. The benefit here is that I'm just solving a one-dimensional problem. And then often what happens is that the error can be smaller. And you will typically see here that the radius is just dead flat. There's basically no oscillation here. And the energy is also conserved with the constants which I have. And one of the benefits here is also that kinetic energy is conserved. So if I just plot this one, just the kinetic energy, and take away the potential energy, you will see that since the radius is constant, this is just an initialization problem, but then it's actually equal to 0 in that specific case, because we put the initial velocity here to 0. So that really, no, that shouldn't, no, wait, this is actually wrong. This shouldn't be so. This energy should actually not be 0 here. Okay, I need to fix that one and just figure out what I'm doing wrong. So maybe, oh, maybe it's because I took away the, yeah, I need to take this one out. I'm just going to check this afterwards. So I need the centrifugal barrier in the kinetic energy. Okay, so this is the kind of behavior you're going to see when you solve the exercises. And when it comes to the last exercise, which is you transforming an equation into an elliptical orbit, I just wanted to give a kind of hint there by looking at where we ended on Wednesday. So I'm going to show you a parallel calculation to the one you're going to see in exercise number 4. So exercise number 4 is you doing lots of exciting mathematical manipulations, algebraic manipulations. But I wanted to show you how you can actually do that for the more interesting case with elliptical orbits for the gravitational problem. So I'm just going to take 5 minutes and I'm going to sneak that in. And then on Monday, this is where we will start, when we analyze the type of motion which we can get from a gravitational force. And this will be also relevant for the midterm, because you will have a question where you're being asked, what kind of motion do you expect from a gravitational problem? So let's take a look at where we ended on Wednesday. And let me just bring this up here. And this is where I will end today before we move on to exercises. So let me just bring this up here. And this will be the last thing we do today before we start solving the exercises. So what we did on Wednesday was actually to find the solution of the equation mu times the acceleration, the radial acceleration, which was given by the gravitational force, plus this centrifugal barrier, which went like mu divided by r cubed. So what we found then was that r of the angle phi is given by a constant c divided by 1 plus this constant which we call the eccentricity. And if we put epsilon to 0, that led to circular motion. So we could actually, by just putting that constant to 0, we could extract immediately a circular motion. So that means that the radius is a constant. And we found also that the radial velocity, the angular velocity, was a constant. Now, what we have is that x in polar coordinates is given by r times cosine phi, and y is given by r times sine phi. And the thing we did then was simply to multiply away 1 plus epsilon cosine phi with r of phi. So what we did then was to simply write this like an epsilon. Let me just write this properly. So we have plus an epsilon over cosine phi multiplied with r is just equal to this constant c. And then we know that r times cosine phi is the same as x. So we could rewrite this as r plus x times epsilon equal to c. So what we did then is simply to plug in this expression in here and here. And then we squared the two sides. So we moved over x plus x times epsilon. We moved that over to the right-hand side. And then we squared r squared, which is the same as x squared plus y squared. And then what we got then is that this is equal to c of c squared plus epsilon squared times x squared minus 2 times x times epsilon. And then we rewrote this again in terms of x squared, 1 minus epsilon squared. And then we have plus y squared. And when we add this other constant, 2x times c, plus 2x of epsilon times c, and this is equal to c squared. The next thing we did, or rather which we are going to do now, is to simply define a new constant. But first we divide by this quantity 1 minus epsilon squared. So what we get then is something which runs like x squared plus x squared here. And then we have an expression here where we also define d, a new constant, which is c times epsilon divided by 1 minus epsilon squared. So we divide by that, and we have a term here which is going to have a 1 minus epsilon squared. So we rewrite this as 2 times d times x plus y squared divided by 1 minus epsilon squared. And this is the same as c squared divided by 1 minus epsilon squared. Now you may ask, I mean, how do we find elliptical orbits from this? So one thing is to complete the square. So we add plus d squared on both sides. If we do that, then we can bring this together with this term, and we can rewrite that as an x plus d squared plus y squared, or 1 minus epsilon squared. And this is equal to c squared, or 1 minus epsilon squared, plus this quantity d squared. Now, it doesn't look like as if we have gained much, but now we are going to do a further manipulation, and we are going to define a new constant, which we simply call for a squared, which is now given by c squared divided by 1 minus epsilon squared. And now this is also squared. And if I do that, then what we can find then, if we now look at the term which we have on the right-hand side, this term here, this is a term which I now can rewrite as follows. So if you look at what we have here, I multiply with 1 minus epsilon squared. So I can rewrite everything which we have here as x plus d squared plus y squared, or 1 minus epsilon squared. And now I bring together the constants which I have on the other side, and I define a new constant. So I'm going to define a constant, and you can actually, if you now look at the expressions which we have, so this quantity d, which we defined here, this quantity is nothing but if I take and square that quantity on the other side. So what I get then is a c squared, or 1 minus epsilon squared. And then I have this quantity d squared. So if we scroll down a little bit, d squared is going to be c squared epsilon squared divided by, so I'm going to get c squared epsilon squared divided by 1 minus epsilon squared squared. And then I'm going to collect terms. I define a new variable, which we have defined here, this term here. And you can see that you can rewrite what you have on the right-hand side in terms of this constant a squared. So this is actually going to be equal, this right-hand side will be equal to a squared. Then I divide by a squared on both sides. So I get an x plus a d divided by a, and this is squared, plus a y squared, or 1 minus epsilon squared times this constant a squared. And I can rewrite this in terms of a new constant. So now you're asking, where is this guy going with all these constants? So I can define a new constant, which is given by b, which is simply a times 1 minus this epsilon squared. So if I do that, I can rewrite everything as x plus d divided by a squared. And then I have plus y squared divided by b squared and equal to 1. And this is nothing but the equation for an ellipse. And I guess you've seen that in some of the analysis courses, the equation for an ellipse. This is essentially that equation. And you can make a plot of it. And this is where we're going to stop today. So if you take and make a plot of these terms which we have, you could now think of this being the middle. And then you have a point here. Oops, this should be have the same distance. So this is a center point. And then if I now look at another point here, so you can now think of the sun. If this is the Earth-Sun problem, you could think of the sun being here. And this distance which you see out here is the one which we called R-min on Wednesday. And the distance which you have over here is this distance which we called R-max, the maximum radius. So this is the aphelion. R-min is the perihelion. This is the center of this is actually the same distance between the two points. What we will have then, if we now go back to these expressions which we put, the distance here is going to be the distance x, and the distance here is going to be this distance d. And then we can then plot this ellipse, which is going to look something like this. And again, you can see my fantastic drawing skills. This quantity b is given by this distance from the center to the point here. And the point C, on the other hand, is actually given by this distance between the mass center of the two objects and to the surface of the ellipse. And then we would have an angle phi, which goes from 0 to 2 pi. So this quantity R-min is normally what we call the perihelion. That's the shortest distance between the Earth and the Sun. And this distance here is normally what we call the aphelion. And what we are going to see on Monday, and this is where we stop today, when we have this eccentricity equal to 0, we are going to have a circle. That's a circular motion. The total energy of the system is less than 0. So that means that we have a bounded orbit. So the system doesn't escape from that orbit. So we keep orbiting around an object. So that's a bounded orbit. And on Monday, we will see now that if epsilon is larger than 0, but less than 1, then we get an ellipse. The energy is still less than 0, and we have a bounded orbit. And what we will also see on Monday is that when epsilon is equal to 1, then we get a parabolic motion or parabola. And we have unbounded motion. And the energy is going to be exactly equal to 0. So that means that there's a balance between kinetic and potential energy. So this is an unbounded orbit. And finally, when epsilon is larger than 1, we're going to have a hyperbolic orbit. The energy is going to be larger than 0. And we are going to have an unbounded orbit. So we are going to see that next week. And we are going to link many of these observations with the midterm, which will be available on Monday from next week. So on Monday, we are going to start here, and we're going to demonstrate the link between the energy of the system and these observations concerning the type of orbits which we have. And we will also show that when epsilon is equal to 0, you will get a parabola for the motion. And when epsilon is larger than 1, you will get a hyperbolic orbit. And these will correspond to unbounded systems. So that means a comet coming in close to the Earth will be deflected and then just disappear from the Earth after some time. So these kind of motions are things we will explore in the midterm. And we will check that the energy is conserved, that angular momentum is conserved, etc., etc. And then the next step in the midterm is actually us building up a code for the solar system, where we add one planet at a time. This is, I used a little bit more time, but I just wanted to wrap up the first part of the type of motion we get. And now we spend the rest of the time solving the exercises, if that's okay with everybody. Any questions so far? Okay, I'm going to switch off the recording, and then we just move on to the exercise solutions. And for those online, Shu Yu will also help you with the discussions of the exercise.